evening and welcome. It's Monday, it's time for the mathematics news. This afternoon we're talking about work, energy and power, and I want to spend a little bit of time just talking about what these concepts are, and then I want you to go away and think a little bit about what these concepts are. These are very specifically maths and physics definitions of these three things. Work is what we're going to deal with mostly today. Work is defined as the product of a force and its displacement, and that boils down to a very nice simple formula. If you're looking at the amount of work done by a force, it equals the size of that force multiplied by the displacement of that force. So if you're moving a box over a certain distance, for example, if you push it with say 13 newtons and it travels over the course of 3 meters, then the work done is equal to the size of the force times the distance travelled. And it has to be in SI units, it has to be in newtons, it has to be in meters, and that gives you the amount of work done, which is 39, and that's measured in joules. Joules is a measure of energy. It's the units, the SI units for energy. And energy can be lots of different types of things. You can have kinetic energy, you can have potential energy, you can have work done, which is a type of energy, you can have heat energy, you can have light energy. And we're going to use the term energy to describe mostly 3 different things: work done, kinetic and potential. But in general, you can think of energy as being the property of something that enables it to perform work as defined above, as being the force times the displacement. So we're going to be talking about things which are in motion horizontally, the energy of the kinetic energy of something that's in motion, or the potential energy of something that's falling. And all of these things, work done and energy, potential or kinetic, it's all measured in joules. Power is going to be later on. We'll come back to power in a separate video. But power is the amount of work you do over time. And so a more powerful engine can do more work. And the formula for power is equal to work done divided by time. And work done is measured in joules, which is usually a capital letter J, and power is measured in watts, which is usually a capital letter W. And we'll come back to those, come back to power, but we're going to talk mostly about work done today. And you have different formulas which are going to help us solve problems. First of all, work done is equal to force times displacement. That is just going to be used all the time. But we're also going to have things involving kinetic energy. So like I said, that's a type of energy where something is in motion. If something is moving, it has energy because it's moving. And the formula for kinetic energy, which you might have come across before, is half mv squared. And the v is the velocity of the object, the m is the mass of the object. So if something has a mass of, let's say, 80 kilograms, could be a person on roller skates, and they're traveling at 3 meters per second, then their kinetic energy is just a half times 80 times 3 squared, which would give us 40 times 9, which is 360 joules. It's interesting to compare the amount of joules in different things. So this person who's moving, not too fast, 3 meters per second, they've got an energy of 360 joules. And if you compare that with something that's much heavier, they would have more energy. If you had something that was heavier but going much slower, it might have the same amount of energy. But we can transfer the energy from one thing to another. So if something starts to fall, it has potential energy to begin with, but it loses it as it falls, but it gains kinetic energy as it's falling. And all of this energy in the problems we're dealing with is going to be contained in one sort of situation. And it gives us a way of working out missing numbers, which is what the M1 questions boil down to. We have a situation where we have the total energy at the beginning of a question. Okay, so you start with some either kinetic or potential energy at the start of something, and then over the course of the journey, or falling or moving to the side, we add in the amount of work done by forces involved. So that could be the force of an engine, it could be the force of somebody pushing, it could be anything that's sort of driving the object forward. So we add the work done. I'm just going to do WD for work done by, let's say, driving force. And like I said, that could be the engine of a car, or it could be a person pushing. But as we do that, there's often resistance, there's often friction involved. So you could have the work done by the driving force, but then we take away the work done against the direction of motion. That's the work done by resistance. And if you have this at the beginning, you're getting more energy from the work done. You're losing some energy because of the resistance, but overall, everything will add together to be the total energy at the end of the problem. At the end. And we can use this sort of formula to solve every single problem that crops up in the M1 energy style. We have this at the beginning, we add in the work done by a driving force, we take away the work done by resistance, and at the end you have the total energy that's left over. At the beginning this could be kinetic, it could be potential. At the end it could be kinetic, it could be potential, but whatever we have in this part of the equation, it all comes together to give you the total energy at the end. Okay, so let's have a look at some questions. We're going to start off small, and these are very much like the exercise I want you to do today, which is exercise 9A. And exercise 9A has some simple questions and some more complicated questions, and eventually they start adding in resistance, and they have different types of kinetic energy, either at the beginning or the end. But let's have a look at a simple question. So here we've got Peter is pushing a 44 kilogram box 3 meters across a rough surface, and there's resistance involved. So there's resistance on this surface, and the resistance is pushing back at 145 newtons. So Peter is pushing one way, the resistance is pushing in the opposite direction, and the box starts and finishes at rest. And this phrase here is telling you something about the energy involved. So if it starts and finishes at rest, that means the energy at the beginning is nothing, and the energy at the end is nothing. So Peter pushes against the resistance force, and we want to work out how much work is done by Peter. And like I said before, work done is always the force multiplied by the displacement. So in this case, we need to try and work out excuse me, the size of the force and the displacement that Peter had to push this box over the course of 3 meters. So we have the energy at the start. So at the start, there was no kinetic energy and there was no potential energy, because it wasn't moving. The potential energy, we don't really have to worry about that too much at the moment. Potential energy is going to crop up in questions where things are falling and we're given like heights of things. So if somebody has an object and they drop it from a height, then we're going to end up with potential energy. But all of these first questions in this first exercise, really, we don't need to worry about that at the moment. It's only when we start having things dropping from the sky or rolling down a hill. But at the beginning of this question, there is no energy at all. We're interested in the work done by Peter. We're going to take away the work done by resistance. And at the end, we have nothing either. We have no kinetic energy, we have no potential energy. So we use this to form an equation. We can work out the work done by resistance because we were given the resistance size and we were given the distance travelled. So here we have 0 plus the work done by Peter, take away the work done by resistance, which is 145 newtons times 3 meters equals 0. And so the work done by Peter is just that, really. To overcome resistance, to start with 0 and finish with 0 energy, we end up with 435 joules. And that was the amount of work done by Peter. the force that Peter had to push that box was exactly the same as the force of resistance in this particular case, because there wasn't any sort of increase in energy by the time we got to the end here. Let's have a look at a similar but slightly different situation. So I want you to imagine Amelia is pushing the same box. Who's pushing this box? Why are we doing this? I don't know. But at the beginning of this problem, it does start at rest. So Amelia is pushing a 44 kilogram box 3 meters across a rough surface, and there's a resistance force of 145 newtons again. The box starts at rest but finishes with a speed of 4 meters per second. Okay, how much work is done by Amelia? So at the beginning of this, because it starts at rest, we have at the start no energy. Okay, and then we have the work done by Amelia, which is what we're looking for. Let's call that work done by Amelia. We're going to take away the work done by resistance, which again is 145 times 3 meters, which is 435 joules. And at the end, we have a speed of 4 meters per second. So we can calculate that. The kinetic energy here is kinetic energy is always 1/2 mv squared. Okay, so here we have a half times the mass of the box, which is 44 kilograms, times the velocity at the end, which is 4 squared. So the kinetic energy at the end there, we've got a half times 44 times 4 squared. Where's my calculator? 0.5 times 44 times 4 squared gives me 352 joules at the end. So then we can sort of form an equation from this. We've got 0 plus the work done by Amelia, take away 435 with the resistance, equals 352. So the work done by Amelia is 352 plus 435, which gives us a total of 600. No, that's not right. Must be 700 and something. 352 plus 435, which is 787 joules. And if you compare this to the box that Peter was pushing, where's my working for Peter? I've lost it. But there is more work done by Amelia, because by the end of the whole journey, I can't find it. By the end of the journey, Amelia had pushed the box so that it was moving faster, which means she had to put in more work in order to create more energy. So there was much more going on here. Peter only increased it by 435, but Amelia, the work done was 787. Let's have a look at another one. Okay. This time, it's the same box pretty much. I'll just use the same piece of paper. This time, Emmanuel is pushing the same box 3 meters across a rough surface, but this time the box starts at 2 and finishes at 4. So we can have some energy at the beginning. So here at the beginning, we have the kinetic energy is a half times 44 times 2 squared. Then we're going to add the work done by Emmanuel. We're going to take away the work done by resistance, which is 435. And at the end, we still have kinetic energy because it's still moving, but it's moving faster. This is a half times 44 times 4 squared. So putting that together, we get an equation, and we have the kinetic energy at the beginning is 22 times 4, so that's 88 joules, plus the work done, take away 435 from the resistance, and it equals 352. It's the same speed that Amelia was pushing at it. And then we solve this equation, and it comes out to be that the work done by Emmanuel would be 780, oh no, that's the last one, 699 joules. Okay, so it's 352 plus 435, but take away the 88 from the beginning. So the person who did the most work here was Amelia with 787. Peter didn't have to do that much work because it started and finished at rest. Amelia started at rest but had to get it up to a speed of 4 meters per second. And Emmanuel started, it was already moving, and he got it up to 4 meters per second, so it wasn't quite as much energy needed. But this process works for pretty much every single question. You think about what happens at the beginning. the work done by the force, then you take away work done by resistance, and you're left with the energy at the end. Okay, I've got a couple more questions. Let's just have a break here.
Go. Go.
Okay, my next example is going to be dealing with something like a larger scale. We end up with really, really large numbers in these ones. This is going to be, Catherine is on a train. It's an 11-ton train, so it's massively more heavy than the stuff we were doing before. And these sorts of questions, when you have massive trains or cars or things involving tons and engines, the numbers become very, very big. It's surprising how big these numbers are, and you can lose track of the zeros. You have to be very careful with the different numbers you're dealing with. If you lose a zero here or there, then your whole question can go wrong. So be careful. Type them into your calculator, count up the zeros if you've got an answer, double check things is my advice. But the process is still the same. Here we've got Catherine, she's on an 11-ton train. She's traveling initially with 5 meters per second. It speeds up to 12 meters per second over the course of 1,000 meters. What is the work done by the train's engine if there is a resistance force of 50,000 newtons? So we put it into the same sort of stuff. We have the energy at the beginning. The energy at the beginning is the kinetic energy, 5 meters per second. So that's a half times the mass of the train, which is 11,000 kilograms, times the velocity squared. We're looking for the work done by the train's engine. I presume Catherine's driving this train, but we're looking for the work done by the engine. And we're going to take away the work done by resistance, which is 50,000 is the size of the force, but it's happening over 1 kilometer. So it's 50,000 times 1,000 meters. So 50,000 times 1,000, and that equals the energy at the end. It's still got the same mass of 11,000, but now it's going at 12 meters per second. And it just forms an equation that we can solve relatively easily. Here we have, again, like I said, big numbers, 137,500, plus the work done, take away that number. Sometimes it's quicker to type this into your calculator as standard form, or scientific notation. That's 5 times 10 to the power of 7. And this comes out to be, the kinetic energy at the end is 792,000. And then you just add that to both sides, subtract that away, and you're left the work done by the train's engine, which in this case comes out to be 506,54500 joules. But you could shorten that down to kilojoules. So kilojoules is just this divided by 1,000. So there's 1,000 joules in 1 kilojoule. So sometimes in the back of the book you see answers in kilojoules. And also we only need 3 significant figures. So I'm going to write this as 5.06 times 10 to the power of 1, 2, 3, 5, 6, 7. Or that's in joules. Or you could even do 5.06 times 10 to the power of 4 kilojoules, just dividing that by 1,000. It's worth noting that on your calculator, you can usually on scientific modern calculators type that in like that, but you can also type that number as 5E7. That's the quickest way of doing it. If you've got an E button on the Texas calculators, it's this one here. It's got 2 little E's, 2 capital E's. And the Casio buttons are something similar, but they might be in a different place. Well, they're definitely in a different place. So that means, what is that? 50 million? Yeah, 50 million. So let's do one more question. So this was very similar to the boxes, but eventually they start asking you about things involving the forces. Maybe you're missing one velocity, or maybe you're missing one of the masses, or maybe you're missing the size of a resistance force. And you piece it together in this way, and you can find out the missing numbers. Eventually, again, we'll have these going up hills, but let's just deal with things going left and right for now. So now, Leslie and Gloria are driving a 1,800 kilogram sports car. They can't both be driving, I'm not sure who's driving, but they're in a car, and it travels from rest, and it speeds up to a ridiculously fast speed, 80 meters per second. I worked that out in kilometers per hour earlier. It's something like 220 kilometers per hour. And this happens over the course of 200 meters. If the driving force of the engine is this, that is actually 2 times 10 to the power of 7 newtons. What is the resistance force? So again, we piece it together. we put everything we know in. At the beginning, we have no energy. There's nothing moving because it starts from rest. Okay? It starts from rest, so we know that kinetic energy at the beginning is 0. There's the work done by the driving force of the engine. We're going to take away the work done by resistance. I'm going to call that work done by the driving force. And then we're going to take away the work done by resistance. And at the end, it's going at 80 meters per second. So 1/2 times the mass of the car, 1,800, times 80 squared. Okay, we are told the driving force of the engine is that. So if we want to work out the work done by the driving force of the engine, it's going to be this multiplied by the distance travelled. Work done is always the force times the distance travelled or the displacement. The 0 doesn't matter anymore. So we've got 2 times 10 to the power of 7 multiplied by 200. Take away the work done by resistance, that's what we're looking for really. Once we've got the work done by resistance, we can find out the size of the resistance force. And this number over here comes out to be 576.0000. Again, be careful with the numbers of zeros. And if we add that to both sides and subtract that from both sides, this one, what's that? 2 times 10 to the power of 7. Times 200. That is a ridiculously long number. So it's 4, and then 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Minus, that is 5.76. 1, 2, 3, 4, 5, 6 times 10 to the power of 6. It's the work done by resistance. So the work done by resistance comes out to be 399,424,000. That's in joules. But that isn't what the question here asked for. It wanted the size of the resistance force. So in order to work this out, we're going to do the definition of what work done is, which is the size of the force times the distance travelled, which was 200 meters. And that means we can get the force of the engine, which in this case is 199,712,000 newtons. Or to 3 significant figures, that would just be 2 times 10 to the power of 1, 2, 3, 4, 5, 6, 7. Well, I suppose 2.00 times 10 to the power of 7. And that's a force, so it's measured in newtons. And the questions in exercise 9a are a lot like this. But if you have this process, you say the energy at the beginning plus the work done by the driving force or the pushing force or whatever the thing is, take away the work done by resistance, if it exists, it might not do, is going to equal the energy at the end. And all of these questions are going to end up being like this. At the beginning there's some energy, and at the moment it's just kinetic. The next set of questions will have kinetic and potential. Then we have work done, then we take away the resistance, work done, and then we get the energy at the end. And you form an equation and you can find out what happens. Good luck. Exercise 9a, that's the way to go. From the Mathematics News Desk, good evening.